Okay, let me see. May have been. All right, that is because in the other one I had in the other class, why did this change? Okay, let's look at the other class. That may have been a problem in that case. See, in the other class, I had exactly this with 3 centimeters. That makes sense, isn't it? That's why you had problems, all of you. And I thought I had exactly identical. Okay, I will solve the problem. I will remove, I will give you for all of them, your maximum is gonna be your participation, and it's gonna be the maximum for the exercise, all right? And then we'll move it, because it is true, 10 is not right. I kept looking at this one for some reason. I don't know, I apologize. I don't know why the other one came to be different. At some point, there was a mistake. I don't know when, because I uploaded those in the fall. I cannot even recall. Okay. Now I'm gonna solve it, and then, as I said, I need to make a note, and I will correct the maximum. All right, so let's go back. This is the correct. This is the correct, the 3 centimeters. All right, and that is the solution, as a matter of fact. That's why I thought, why in one class they did it well, and the other class they had problems. All right. So how would you solve a problem like that? Now, now you see the correct solution, all right? Usually in a problem like this, what I would do is the following. We know from the class that the way we find the velocity of the wave, all right, let me start with the velocity, phase velocity. We find the phase velocity of the wave by taking the phase, all right? I mean, let me consider a general case now. The case of a wave cosine omega t minus beta x, all right? Let's assume that you have this general wave and a different, let's call it G, this one. So it's different from the above. Okay. And the way we find the phase velocity is by taking the phase, which is omega t minus beta x, differentiate that with respect to time, and and place this equal to 0. This is the equation we are solving. Now, if you differentiate that with respect to time, that gives you omega minus beta dx dt. So this is the way we find the phase velocity. And this is equal to 0. And from here, we find dx dt equals omega divided by beta. And this is what we call phase velocity, all right? Now, what we know is that every wave that has this form, which is a harmonic wave, and propagates in free space, what did we say? That the phase velocity is going to be the velocity of light in free space. Did we say that? So practically, omega over beta is going to be the velocity of light in that medium, which is free space, which is for us is what? 310 to the 8 meters per second. Okay? All right. What is omega over beta? Omega is 2 pi f. What is beta? Beta is 2 pi over lambda. You remember that? F is frequency, lambda is the wavelength. So if you take the ratio of the two, is equal to F times lambda. So what do we find from these two? That F times lambda equals C. And therefore, you can see which of the three solutions satisfy that. And it's the last one with 3 centimeters, all right? Yes.
On the quiz, were we given that omega over beta equals C? Is that something that's true for every single?
Yes, and I remember in class, if I remember, we also talked about that. If I go back, and then also I told you, remember, on the basis of that for 1 gigahertz is 30 centimeters. For 10 gigahertz is 3 centimeters. Remember, we had that list. If I can go back and find it for a moment. I am right here. We talked about that at that moment. And then I talk about losses. But all of these waves propagate with the velocity of light. And that's why we use this here. And I remember, at least I told you, to keep that in mind and do it quickly so you don't have to calculate the velocity of light and then try to get this. That's how I remember it practically. Okay. How about, so for this one, I will make the appropriate corrections. As soon as I go back to my office to the exercise, I will put the maximum to go to participation. So those who participated will get the maximum for participation. So that's gonna make it accurate. As a matter of fact, I can do this here, I believe. But I need, anyways, I don't wanna spend more time. I will do it in my office. Now, there was a second part, and I believe, do you have any questions about the second part? Let me go to your, this is 502, okay? Second part. Okay, second part, we had good participation with the exception of 21 people who said A. The correct answer is C. Do you want me to solve that one? You know, okay. Do you want me to solve it? Yes, yes, okay. All right, let's go to that one. This one. What did I do? What did I do with the other one? Disappeared. It's okay. You know, I somehow it disappeared, or maybe it has not disappeared. I don't know what it is. But do you want me to upload the solutions for the problem? I can rewrite them. But in any case, let's try to look at this one now. This one gives you a wave that is f, if I remember well, f of t comma x equals 4 sine of omega t minus.
It's 10t minus x.
10t minus x. Okay. And then it asks you to find the Phasor form. All right, so this one, you can rewrite it as a cosine of pi over 2 minus 10t minus x. So you can write it as a 4 cosine minus 10t plus pi over 2 plus x. You can rewrite it as 4 cosine 10t minus pi over 2 minus x. All right? So what is the phasor for that? It's going to be 4e to the minus j pi over 2 minus x, which is going to be 4e to the minus j pi over 2 e to minus x, which is going to minus jx rather, which is going to be what? 4 minus j e to minus jx. See. Any questions about that? Okay. Just conversion of these two phasors. Yes. When you go phasors, it disappears. All right, because the phasors, we define them like this. The real part, excuse me, the phasors defined like this. F is the real part of a phasor. All right, that is the definition of a phasor. So if F is cosine, for example, of omega t minus j beta, and then, excuse me, this one here, sorry, plus times 8 times. That's the definition of the phasor. So if your phasor F, to be able to get the phasor for that, so F by itself is the real part of e to the j omega t e to the minus j beta. So in this case, if you compare these two, it implies that the phasor is e to the minus j beta. Okay? So practically, if I have the phasor, going back, if I have this phasor, so my f, the real function of t comma x, will be the real part of v to the j omega t times the phasor all right, which is going to be 4, and then a cosine. J minus j is e to the minus j pi over 2. All right, so this one is the, put it on top. This one here is e to the minus j pi over 2. So that is cosine, the real part of this is cosine omega t. I got the 4 in front. And then you have minus pi over 2 minus x. And this one will give 4. And then you can take this one cosine pi over 2 pi over 2. And then you have minus omega t minus x plus x, sorry. And that makes it 4 sine minus omega t plus x, or in fact, you can, I wrote that as minus plus. No, I have, excuse me, I made a mistake here. So I change omega t, I change omega t pi over 2 negative, and this one has to go there. Okay, now we are correct. So here, for that case. All right, that's how we go back from the phasor to the real time. Okay, that's quiz. So remember, 10 to. Yes.
So can you re-explain how you get the real value of e to the negative jb, but j is still an imaginary? So yeah, how do you get the real value of that being imaginary?
I did not get the real value of that. The real, so you mean you're talking about, let me see. You're talking about moving from here to there.
Of by the f lowercase f equals re of e to the j.
Yeah.
How about that?
Yes. The real part of this is a cosine.
That's the one above that. Yeah.
That's a phasor.
The re above that as well.
This an exponential has a real and an imaginary part. E to the jx is cosine x plus j sin x. So the real part of v jx is cosine x. Is that what you're asking? Okay. Any questions? And how much is cosine by itself? Cosine x equals 1 over 2 e to the jx plus e to the minus jx for that reason. Remember those properties? And sine, how much is sine? E to the jx minus e to the minus jx. Let me see. Yeah. Any questions? These are the properties. Okay. If I find, I will probably find the other also solution. Do you want me to? I was trying to think, you know, whether there is an opportunity in that. I have not used it before, but whether I can put in for the accurate solution a short given explanation within. If I can do that, I will start doing this instead of trying to post all of the solutions for the quiz. In fact, if anybody wants to do for me the solutions for all of the quizzes, I'll give you points. Seriously. If you can write down the solutions for all of the exercises, let me see. I will send an email and I will tell you how many points I'll give you. So it can help me to put the solutions on the web. All right. And then for exercises and then for quizzes. Okay. Because I need some help. I don't have the graders are not electrical engineers. So they cannot do that. All right. They can grade, but they are electrical engineers, but not, they don't know this stuff. They are in computer science. They don't know math very much. I'm sorry to say that. but they don't remember complex numbers and stuff. Okay, any other questions before I go to our problem? All right, so today, what we are going back to transmission lines. Last time we did a review of transmission lines. And what we said to remind you is the following. We said that, remember when we showed that, it's not in the phasor domain. Even if we write a phasor domain here, when we show that, it's just to give us an idea of how in the time domain, in one point in time, the wave is going to show along the line. If, say, for example, I had many voltmeters along this line, and I would measure the wave at one point in time, then I would see something like that along a line which is in fact infinite long. All right, I would see only this. That's what we said last time, like here. If I have a line which is infinite long, assuming that there's no termination like here, but it's infinite long, then the wave that is excited here by the voltage source in one point in time, this is the source, all right? This is not the wave, this is the source that excites. The source is a cosine omega t, all right? And then it varies over time. Now, if at one point in time, t equals, say, t naught, I have many voltmeters here and I measure the voltage, then I will see this, exactly. That's how the voltage goes if there is nothing to abstract it. All right, to abstract, to create like a barrier here for the voltage to continue. So if it's infinite long, that's what you're gonna see. And we call that the incident wave, all right? And we said last time, we indicate that with a V plus in the phasor domain. In the time domain, the incident wave, which is this, is gonna be cosine omega t minus beta z. All right, beta is the propagation constant as we defined it last time. Z is this length, and z is along this direction. And at time t equals 0, we have this, all right, along the line, and that's what you see here. Now, in a phasor form, this is in the time domain, but in a phasor form, time is not present anymore. We got rid of time, all right? So what you see here in a phasor form is gonna be the line infinite long, and the wave, which we call the incident wave, is what is created by this voltage source. This wave has this form, has a constant, and has a phase, all right? It has a magnitude, so it's a complex number. It has a magnitude, which we indicate by V naught plus, and has a phase, all right? And if we take this expression, xz equals 0, where z equals 0, then this incident wave has to be exactly the voltage that applies here at AA prime. But what voltage applies there? The source. So practically at AA prime, this wave, where z equals 0, and therefore this, all of this becomes 1. The wave here has to be equal to Vs. So practically, the incident wave at z equals 0 has to be equal to the voltage source in the phasor domain, which is just the amplitude of the source, all right? Because the cosine is not there. We remove that cosine we had in the time domain. So it's just the voltage source. which is measured this one in volts. So this, in fact, gives only for that case, for the infinite line, the magnitude of the incident wave. So now, since we saw that in the time domain, all right, this is, and it starts at Bs. You see that I've started here at t equals 0, cosine is 1. So I've started it at Bs value, and then it starts moving as a cosine forever. Now this is how it looks in the time domain, but in the phasor domain, because we are moving away from the time domain, you're not going to see time domain for much longer, you know, in this class. So we need to, I'm using always time to help you make the transition to the phasor form. But in the phasor domain, right, where this is our incident wave, where at this point is equal to Vs, the phasor, in the phasor domain, this is the magnitude of the wave. The incident wave in the phasor domain has a constant magnitude and is equal to the source that creates it, to the value of the voltage source that creates it. All right, that it keeps going, that's the magnitude. Okay, so now I have another magnitude. And in fact, one more thing that also I would like to introduce here. Because in the phasor domain, we have beta z, all right, and beta, let me put it here. So to make a parenthesis, beta, so we have a wave which has a magnitude and phase. We can write the phase like that, remember? Beta is 2 pi over lambda. So practically here, the phase beta z is nothing else but 2 pi z over lambda. So practically, I don't necessarily need to know the exact value of z in physical units, centimeters, meters, and the value of lambda. I just need to know the electric length, like how long is z in wavelengths. And that's the only thing that matters for the phase, the electric length. So from that point on, everything on the transmission line is going to either be given in electric lengths, or if I give you the physical length, and you will have to find the wavelength and then change all of your physical lengths to electric lengths. So it's very important in the phasor domain to work with electric lengths. So the velocity of the wave is here again. We talked about that, all right? About this formula, very fundamental, and you need to remember it. Okay, so now, since I plotted the magnitude of the incident wave, I want to plot also the phase. The phase of the wave is minus beta z, which means it is minus 2 pi z divided by lambda, as we saw before. So it's a constant 2 pi times whatever is the value of this z, because it's in lambda, electric length. And therefore, it's going to be just a straight line, all right? Since z, it's a linear function of z. So it's going to create a straight line that is going to become more and more negative as z increases. So when people plot the phase of that incident wave, they're going to show it like this. Or because 2 pi and 0 are identical on the circle, all right? They give the same values. So an exponential of 0 and exponential of j2 pi is the same, all right? Then a lot of times you will see it like this, like a zigzag. But this red and this one are identical. You got that? Okay. So a lot of times in books, you will see it like this. And then the only reason they do that is to save space. And then you will see it many times when you arrive at 2 pi, then you can see it in graphs, and it drop to 0 for that reason, right? So in an incident wave, therefore, we have an infinite line. We have this type of propagation, only an incident wave, nothing else. Now, an infinite line is like a very, it's an idealistic kind of situation. Does not apply to practical cases. In practical cases, we'll always have a line that is terminated. And we are gonna look next at 3 very important terminations. One is the matched case where the load is equal to Z naught, characteristic impedance of the line. Do you remember the characteristic impedance of a line? How do we define the characteristic impedance of a line? Do you remember? The characteristic impedance of the line is the ratio between V naught plus and I naught plus, right? And how is it? Is there an entity though? Do you remember it's the square root of what? Over C. So for a given line, a given geometry is known what it is. A lot of time, most of the time I will give it to you unless you design it. I will tell you, you have a line of so many Ohm's characteristic impedance, all right? And also I will tell you what kind of frequency we have, which then I will expect you to find all of the dimensions and wavelengths. I will know the wavelength to be another frequency, right? Very good. So if the load is equal to the characteristic impedance of the line, this is called mass, which means there is no reflection. We'll see that. So if there is no reflection, if the line is infinite long, or if the line is terminated at its characteristic impedance. Open-ended line is the one where instead of a load, you just have an open-ended, open circuit, rather. Short-circuited line is the one where instead of a load, you have a short. All right? The 2 ends are connected. And also we define the reflection coefficient. It's a new entity. And the reflection coefficient has a value that changes with Z. Excuse me, with Z. The reflection coefficient has a value that changes with Z. So the reflection coefficient at any point along the line will be the ratio of the reflected wave over the incident. What is the reflected wave? This part, you see already, I have already translated it. And this is the incident. So the ratio of these two gives me the ratio of this wave and that wave gives me gamma over Z. Over Z. You see this gamma L does not have a Z in there. So that gamma L is the reflection coefficient when Z is 0. Is gamma at this point. All right? But gamma reflection coefficient when Z equals 0. All right, and then this is the generic form, the general form for gamma L. So now, with this in mind, I would like to solve a problem. So, and we are going to solve a problem here. At page. A particular example to see how we would do how we would find all of this, how we would solve a line with that has a load. Let's start with a matched load, Z naught, okay? Now look at this. I will then create a line, a matched line. I don't know whether we'll finish it today, but if we don't, we will continue on Friday. So here, matched line. Okay, so then we'll do a thick line like this, right? And then duplicate that. That's our transmission line. And then at the end, we have a load, which is going to be Z naught. Here is the characteristic impedance. I always write it like this, and beta is the propagation constant. I always write those things to see that these are given. And then right here, we have the source. And the source has this value, ds. We are in the phasor domain, all right? So now I'm gonna see what I'm gonna write all of my equations. I know that total V, and see this is Z equals 0, and this is Z equals L. Total V is gonna be V naught plus E to the minus J beta Z plus V naught minus E to the J beta Z. I always start with this set of equations myself, because they are the easier. You don't have to remember everything. And this is I naught plus E to the minus J beta Z plus I naught minus E to the J beta Z. Okay. Now, add the conditions. I have two conditions. One condition is at the source. What is the condition at the source? That V of Z, when Z equals 0, is equal to Vs, right? Which implies here that Vs is going to be equal to V naught plus V naught minus, all right? And then I have another condition at the load. What is the condition at the load? That the total voltage at the load, let's assume that this is the total voltage at the load, and this is the current in the load, all right? So at the load, we have that V sub L divided by I sub L equals Z naught. How much is V sub L? Is V of Z when Z equals this distance, L. And I sub L is I of Z when Z equals L. And this is equal Z naught, okay? And then we have that, we substitute, instead of in this equation 1, and in equation 2, we put where Z, we put L. And we have that Z naught equals V naught plus E to the minus J beta L plus V naught minus E to the J beta L. E to the J beta L. And then we have I naught plus E to the minus J beta L plus I naught minus E to the J beta L. Now, what else do we know? We know that Z naught also is V naught plus over I naught plus. Remember those, we wrote it last time. V naught minus divided by I naught minus. Okay, so practically from here, let's call that 3 and 4. We have one more. We have 3, 4. It gives us that Z naught equals. I have here V naught plus E to to the minus j beta L. I will replace the i's only, plus v naught minus e to the j beta L. And then down here, if you remember, we had 1 over z naught in front of everything. And then we had v naught plus e to the minus j beta L minus v naught minus e to the j beta L. And then from here, we move this one to here. So we have z naught times 1 over z naught will be equal to v naught plus e to the minus j beta L plus v naught minus e to the j beta L, v naught plus e to the minus j beta L minus v naught minus e to the j beta L. Okay, and how much is that? This is 1, equal 1. Now, there is one more thing that we have defined. We have defined that gamma L equals v naught minus over v naught plus. Practically, the incident and reflected waves, you remember this one here, it's equal 0. See that? Remember this. With that definition, we can go here and write, in fact, the other way. Yes, and write the following. Let me see. Yeah. All right, so I will take v naught plus as a common factor in the numerator and denominator. And it's gonna be, therefore, v naught plus, and then I will have e to the minus j beta L plus v naught minus over v naught plus e to the j beta L. And v naught plus here, e2 minus j beta L minus v naught minus over v naught plus e to the j beta L, and I have that equal to 1 from there, you see? All right, now I replace this one by gamma L here. And I also, so practically to see it, this one here is gamma L, and this one here is gamma L, and this is 1. So now, how is that simplifying? That becomes e to the minus j beta L plus gamma L e to the j beta L. And in fact, I will, well, let me do it in 2 steps. E to the minus j beta L minus gamma L e to the j beta L equals 1. So what do I have here? E to the minus j beta L plus gamma L e to the j beta L equals e to the minus j beta L minus gamma L e to the j beta L. What's that? I think let me see. Gamma L. Okay, let me see what I have done. Have I done a mistake somewhere? Minus, I put it here. Let me see, these two go away, but then it should not be 0. Ah, yes, of course it should. Sorry, we are good. So gamma L e to the j beta L equals 0. What does that mean? That means that the reflection coefficient in the beginning of the line is 0. So when the line is matched, when the line has a load that is equal to its characteristic impedance, there is no reflection. There is no reflection on the line. That's why we call it a matched line. And anything that you will do in all of your circuits will be to create a matching, because if there is no reflection of power back to your source, that implies that all of the power that the source sends down to the load is absorbed by the load. Okay, so if your load is equal to the characteristic impedance, there is no reflection. And that is very important condition, because if whatever we have after the end of the line, we will always try to make it, when we design things, to make that load eventually equal to Z naught. So at some point, all of the power is absorbed by the load. All right, so in a matched condition, the reflection is 0. The same thing applies when the line is infinite long. All right. So that now that we've done the matched line, on Friday, we're gonna do the open and the short to see what happens in that case. And I will tell you up front, in that case, the magnitude of the reflection coefficient is 1, which means whatever real power goes down the line is reflected. That's the worst condition. All right. So that's the best. And then the worst, when you have only reactive loads. Any questions about that? Okay, thank you. So on Friday, I will bring also the Smith chart to start getting familiar with it, because that's going to be another.
A quick question. Will you be running?
Yes?
Will there be a talk?
Could you write it? I cannot hear you. So could you write it on chat?